Okay. Hi, everybody. As I promised in the previous lecture, the subject of this lecture is the investigation of the six-hump camelback function. This is a very interesting function. It has only two variables, x and y, or x1 and x2, as given here in its definition. The bounds of the variables are very close. For x1, it lies between -3 and 3, and for x2, it lies between -2 and 2. The minimum values of this function are 6. Two of them are global. The global minimum value of both is the same and equal -1.0316. It is really a very specific value. And the coordinates of the the 2 points generally, where the minimum occurs is either -0.089, 0.71, or we change the signs here, minus becomes plus here, and the plus becomes minus here. So indeed, it is really very specific. If we use this function to test an algorithm and we get these values, this means that this algorithm is really very accurate and could be recommended for other similar applications. We will begin our work by plotting this function in a three-dimensional space as usual. Then we shall introduce to you the contour plot of this function. Then we shall optimize this function by using Pyswarms library. And at the end, we shall animate the motion of the particles in a two-dimensional space and in a three-dimensional space. So at the beginning, as usual, we import the necessary libraries and functions and methods as shown here. We define the function. The definition is given to you here also. And considering the bounds of the function, we define an array x1 which represents the values of the x coordinate between -2 and 2. This is between it comes within -3 and 3. And x2 also is taken as NPI range between -2 and 2. The steps are given equal so that we have equal points, dot 1.5. Of course, the number of the points here will equal 4 divided by dot 1.5. It gives you the number of points. In order to plot the function in a three-dimensional space, we have to use the NumPy mesh grid function. We call it from NumPy. We create a two-dimensional arrays from the one-dimensional arrays x1 and x2. Now we have another x1 and x2. They are shown as capital letters. And now we define the function f of x1 and x2, which represents practically the height or the third coordinate. In order to plot the figure, we define the figure object, we call PLT. From PLT, we call the figure and give an idea about the size which we want. On this figure, we also create the object of 3 axes by passing this word here, projection equal 3D, so that we can have 3-dimensional axis. This is a keyword. And having this, now we can call the plot surface. The plot surface already must be imported. Oh yeah, here it is imported directly. So AX dot plot surface. Plot surface function requires the coordinates x, y, and x2 and z, which is f of x, y, and x2. For coloring, we take color map equal color map cool warm. The opacity here is shown as dot 0.9. In order to show the plot surface with a wire frame, we also add or build a wire frame using the same parameters. Alpha is a little bit different so that the lines will be shown clearly. The row count is equal to 15 and the column count is equal to 15. Also, as usual, because this is a 3-dimensional plot, it is advisable to define the angle or the camera angle by giving a value to the elevation in angles, 45 angles for the elevation, and the azimuth also 25 angles. When we run the program, we shall have this figure as you see here. Let me run it for you. Now it appears. This is the figure of the 6 hump. Look, here is a minimum value, here is another minimum value, here is a minimum value. So there are another minimum value here and here and here. So, of course, there is 6 values. In order to rotate, I have to put here at the beginning mat plot lib and notebook NOTEBOOK. This allows you, if you run it newly, you can rotate the figure as you want. Let us try maybe another time. Overwrite. Run it newly. A message line magic function not found. Matplot, here is matplot, P should be P. Plot matplot lib. Okay. Now it works. Now I rotate it as I wish. Okay, so now we have created the function in a 3-dimensional plot. Here I am trying to show you, I will show you how we plot also the same figure, but with some addition, which makes it possible for you to put the pointer where you want, and you will get there the coordinates of that point, the height, x position value, and y position value. So if we run it here, okay, let me explain something for you. So matplotlib notebook here, it is already written. I have called the necessary libraries and I have defined the function. I have created the mesh grid, and now I want to plot the contour using the new coordinates x1, x2, and f of x1 and x2. Okay, I have created the figure and the three-dimensional axis, and now I plotted the plot surface and the wireframe as I did before here. And in addition to this, I have added this piece of code which allows you to directly measure the coordinates of any point of the figure. So if I press it here and run the program manually, now I have got this figure. Now, if I put the pointer at any point here, maybe, yes, it appears. Here, as you see, these values represent the coordinates of each point. If I put the cursor here, there is an x value, y value, and z pin. If I go to put it here, for example, z is equal 23.1 here in the upper side here. Now here z is equal minus 4.43. This is very useful really because the eyesight is not sufficient to judge about especially the elevation of the points. So this may be useful for you also in additional works. What else we can see? I have also here created for you a general contour for the same function here, but I have added a line statement which defines the number of levels which I need or I request. Levels here is given as NP array between -1 and 1 with a delta value 0.2. So between -1 and 1 equal 2, 2 divided by 2 will give you 10. So practically we will have here 10 different lines, different colors, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And as you see here, the contour really includes 2 points suggested to have the global minimum. And as I told you, this function has 2 global minimum values, but one of them will have inversed signs versus the other, minus AB or minus B and A. So this is one point, and here is the other point, and we shall see these exact values and how they converge here in the next paragraph. So now we have also, we can judge, anyhow, we can get an idea about the position. Look, if the position will be here, so it is about 0 value, but positive value, about 0 from the positive side. This is the x value, and the y value is about 1, but it is negative, minus 0.75, exactly about, it is minus 0.71. If you go up, you will see here this is positive 7.5, for example, and this will be, of course, the negative value, which is displaced relative to this one to the left side of the zero. But the exact value calculation and the exact value where the particles will gather will be seen just now when we optimize the function and animate it in a two-dimensional space. So what we are going to do now. So at first, as you see, we define all the required libraries. We call the functions from the Pyswarms, which may be necessary for us, like plot cost history, so that to see the error and how the error minimizes to the value of 1.03 in minus. And also we need to plot contour in two-dimensional space. And if we want, also we need to plot surface in three-dimensional space. As usual, at first, we have defined the 6 hump function as it is given here. We shall refer to it in the text downwards as a wrapper function. The bounds are between -3 to 3 and -2 to 2 as it is, and it is given variables, names 1 or lower bound, u upper bound. This is the list which represents the bounds here. Okay, now we have defined the option constants which exist in the Pyswarms algorithm. We took C1 equal 0.5 and C2 equal 0.5. They are the same. And the inertial coefficient 0.9. I have explained to you many times the importance of these constants and how to select them. So now we are dealing with one objective function. So we call the single function. From it we call global best particle swarm optimization function, and we pass in it the required information. The required information is the number of particles which we suggest. I suggest the number of particles to be 30. The dimensions are 2 because we have x and y. Options as they are given here equal to options, and bounds are equal to bounds which are here above. So the optimizer now will define, and we can call the optimize function to the function and passing the function which is the wrapper here and the number of iterations. Now we shall get the answer. We shall get the best position, the optimal position of the function where the minimum occurs, and the minimum cost or the minimum error which occurs. If we look what this, when we print, we will print these two values. I think downwards they will be printed, and you will see them. And I told you also, you do not need to print it because the software itself gives you these values automatically when you run the program. Okay, for the sake of animation, we import the object mesher and designer to have a mesh and to customize the x and y values. But as you see, because the bounds between -2 and 2, and because the default values for the designer in this Pyswarms library is -1 and 1, and -1 and 1 come in between -2 and 2, so I kept them. So the limits of the measure are kept the same, -1, 1, -1, 1, and the designer also for x and y and z are kept the same without any change because they are very close and fit within the limits of the function. So what we are going to do now, we shall use the plot contour function. To have a plot here, we need to introduce or to pass the position history. The position history comes from the optimizer. If you call the optimizer dot cost history, it gives you the cost history. If you call the optimizer dot position history, it will give you the position history. So the position history and the cost history already existing from the optimizer. So here the plot contour function, we pass to it the position history by using the optimizer and calling position history from it. We pass the measure. We here add a mark, a point on the graph, which is supposed to be the point where the particles are going to converge. In other words, this is the coordinates of the optimized value or the optimum value. I am suggesting it to have -1 and .7. It could be 1, it could be -.7 and 1.0.1. It depends. I cannot judge. This will be seen when we run the program. Either of them will appear. But having this mark here, the program will show it as an X value with a red mark, which shows you to the degree of coincidence between the position which is given here and the position where all particles will gather. After that, we need to save the animation process so that we can use it later, because I told you this process of animation will take 3 to 4, sometimes 5 minutes. It takes time, and you will not need to sacrifice time always. So it is more practical to save this animation in a file. We call it 6-hump GIF, and we can refer to this file and read this file anytime we want to have an idea about the animation process. Also, we can plot the animation process by using the HTML function directly on the notebook. So, when we run the program, we will have, as I told you, the result of optimization. The result is given to you here. Look, best cost is 1.0316. Look how precise the Pyswarms algorithm is. Really, it is fantastic, exactly as it should be. And the position or the X and Y values are given as you see, -0.089, or you can say -0.1 and plus 0.7. This is minimum, minus this is plus. If you run it another time, maybe you will get this is minus and this is plus. This depends, because we have two global minimum values with different or inversed signs. So the values which we have got now, or which we will get after running the program, these are of course written here because I have already run the program before giving you the lecture. I will run it now so that you will be confident of that. And this is the cost function, as you see, or the error function. Here is -1.2, here is -1.3, which is the minimum error value, which means that it is everything is okay. So, how they appear on the two-dimensional space. Here, as you see, this is the X red value, which is suggested to be the position of, or the coordinates of it will be the coordinates of the optimized value. The black particle here shows the place where all the particles gather or converge. As I told you, they could converge in this position or in this position. Now let us run it for you. Please be patient. It will take maybe 2 to 3 to 4 minutes to converge to the position and to the value which I have told you. Now, as you see, if you look at the notebook here, the Python 3, as you see, Python kernel is running. The dot here black means it is running. And also at the cell here, from the left side, you see this asterisk existing, which means that the algorithm is working on and working on, and it is not yet, it doesn't come to an end yet. We shall watch it. When it comes to an end, we shall go down and have a look at the results newly. I am sure that we will have the same results and the same position or point of convergence. Yeah. Making use of time until it converges, as I have explained to you, really the steps and the work which I am doing here is exactly the same as we did before with the Rosenbrock function and with the holder table function. Really, I wanted especially to show you this function not only because of its specific values and specific behavior, but also I wanted to show you how we can animate this function differently, not as we did with the holder table function or with the Rosenbrock function. With the Rosenbrock function and with the holder function, remember, we have used the position history, which is included in the optimizer. We call the optimizer, and from there we call the position history, and we will get there an array of values X and Y for each particle. As I have told you before, Pyswarms has a specific function where it uses the 2 columns array and create from the Pyswarms position array a third array which represents Z. Of course, how this is done, they doesn't show you how it is done. But in this specific case, now after the program converges here, I shall show you how we animate the 6 hump function. Firstly, by using the 3 or by the 2, column array, which results from the position history, and by using the Pyswarms function to create the Z array. This is one case, which is usually known to us now. And then I will show you how we can do it by deriving the third column in our own way or by our own way. Okay, I think now time is very close. The program will converge and I will show you the results, and then we shall move forward in this lecture to show you the way how we can animate the particle's motion in a three-dimensional space without using the Pyswarms formula or conversion formula. And I want to tell you in advance that the result is exactly the same, no difference at all. No difference. Okay. Well, the annoying thing, as you see here, this time delay, which is taken by the animation process. So although the animation process is really very important and very useful and gives you confidence and gives you feeling of pleasure that everything is working dynamically and so on, but it takes that time. So to get rid of this and to work without it, you need to save the results and work with the saved result. Now you see the asterisk has gone. The problem, the question is solved. We go downwards, we shall see the results. Here, now, we shall see the results newly. The best cost is 1.0316, exactly the same. The XY values are also exactly the same. And this is the cost function coming down up to minus 1.3. And now, as you see here, the particles are still gathering in this point, showing that convergence is taking place exactly in the same coordinates. If you want to see it manually, I can show you that. This doesn't take a lot of time. You go to the file 6 hump GIF. I go here, type it 6 hump dot GIF 6 hump GIF. Here it is. I open the file. Here it is. I double click it. And you see the particles, how they are converging exactly to that point, and very quickly and very precisely. And this is a repetition of the animation. And the same coordinates, this is not 0.75, it is 0.71, as you see, the y-axis, and the x-axis is minus, not 0, minus dot, let me say 1, or like that. So everything is okay, there is no problem, the program is working fine, and we are happy with these results. Now, what is left, I want to show you, I want to go to lecture number, yes, and here now, the title, Optimizing and Animation of the 6 hump function in 3D space. So at first, for those who did not look at the animation of the Rosenbrock or the animation of the holder table, they can also acknowledge themselves with the steps, which are some kind of repetition to the things which I have done before. So what I will go through it quickly because nothing new with it. I will show you only the result, and then I will move to our own way. So we have, as usual, imported all the necessary libraries and functions which are required. We have defined our objective function. We have defined the limits or the bounds of the function. We have selected the values of the constants of the Pyswarms algorithm C1, C2, and the weight W. and then we call the optimizer, and we optimized this function, and at the end we get the optimum position and the optimum cost. Now, in order to plot in a three-dimensional space, we also need to import the measure and the designer. They are imported. Now, as you know, from the optimizer, cost history, we plot the cost history. We did that before. This is the plot, the cost history. As you see, this is the cost history, and it will come to minus 1.3. Here it is, best cost 1.03. As before, but this is just done for the three-dimensional space. Now, what we are going to do, we are going to see the position history. We have to call the position history from the optimizer here, dot position history, which means we are calling the position history from the optimizer. And now, this position history is introduced to the function compute history 3D, which exists in Pyswarms in order to create an array of 3 columns, the X, Y, and Z. It is called position history 3D. This is done by Pyswarms. So if I print position history 3D and I print only position history, I shall get for position history 2 columns, but for position 3D, I will get 3 columns. If I go downwards here, this is position history PH. This is the X, the first particle, X and Y. The second particle, X and Y, and it continues up to, I think it is about 300 iterations. Now, if you go and look how the position 3D looks like, this is the 3-column array, which represents the case by using the converging function, which used these 2 columns to create the 3rd column. The first 2 columns are exactly those which were upwards here. If you look at the first value, 2.389, and you look at it here, it will be the same, 2.389. The second value, minus 1.60, minus 1.60, and so on. So the position array, which is derived from the optimizer, is the same, but the newly born or created array has an additional column which represents the Z column. This is done again by Pyswarms and not by us. Just we applied it, and as a result of that, now we can carry on our animation. For animation, initially we have to define the initial position of the all X values and Y values and Z values for all the particles, for all iterations. So for all iterations, all particles, for X values, this is the index of X, for all particles, for all iterations, all particles for the Z, for the Y coordinate, for all iterations, all particles for the Z iteration, for the, the Z coordinate. Now we have X and Y and Z coordinates. They are in the initial values. And now we want to animate them. So instead of having the initial values, now we will develop the situation for any particle beginning with I equal to 0 to I equal 300 for all particles for the X coordinate. Y history for all iterations from 0 up to 300 for all particles Y coordinate. And the same thing for Z. Now, we use the function offset 3D so that to have the intermediate values of change of the position X, Y, and Z. And that's it. With this now, these are the necessary information for the func animation to work. It needs a figure to be already defined. We have a figure in our case defined. We have an axis. The func animate, here it is, the function animate. The frames, the number of frames, it is given by 300. You can write equal 300 or the position history shape 0. The shape 0 of 0 means gives you the number 300. The interval between the frames is given 150 milliseconds, and I do not want it to repeat animation, just one time. Now, after that, of course, we create a legend at the upper, the location of the legend at the upper left corner here, at the upper left corner. This is the upper, this is left, here is the legend at the upper left corner. And again, I want to save this animation by a name called plot34.gif. The writer for this is the Image Magic. I told you this writer is already installed in the computer. So if I go to plot34.gif here, plot34.gif, and go to the file where it is, here it is, and run it, you will see the particles are gathering and converging to the same point, which is -1, -0. You see? And here, the other coordinate, which is .71. Exactly the same picture as we get when we used the conversion function of the Pyswarms. Okay, with this, I think we have covered in good detail and with most interesting points to investigate the behavior and how to work with the 6-hump camelback function. What is left is to show you how we can also analyze and investigate this function in LabVIEW. This will be done in the coming lecture. This lecture now is long enough, and I hope that within 1-2 days it will be ready, and I shall raise it up on the site in my channel for you to have a look at it. With this, I finish this work. Thank you very much. Wishing you a happy, nice day.